Well done for completing the first 6 sections. You should now be familiar with some of the principles behind resistive loads and their response to the electrical network. Today we will be looking at capacitors, which have an interesting effect on the AC and DC systems. The aims of the course today: to show the effect capacitors have on the AC and DC system, to show how the power factor can be affected by adding capacitors into a circuit, to introduce the principle of impedance. Capacitors have the following details. The symbol is 2 parallel lines representing 2 parallel plates. The label is C. The units are farads, or F. Let's now look at a capacitor. Firstly, what is a capacitor? A capacitor is constructed from 2 parallel conductors, normally 2 metal plates as shown here. We then insert a non-conductive insulating medium between them. The value of the capacitance depends on the surface area of the conductor and the width of the insulation. As the insulation thickness decreases, the value of the capacitance increases. As the surface area of the conductor increases, so does the capacitance. Let's now see how a capacitor reacts when a DC supply is connected to it. Here we have a DC source with a positive and negative terminal, and a capacitor with 2 plates with an insulator in the middle. The Q plus and Q minus represent the charge on the capacitor. As the DC current starts to flow, the positive and negative particles pass on to the plates of the capacitor, and the voltage across it grows. Once the plates are fully charged, the flow of current will then stop. The capacitor remains charged and the voltage potential remains across the capacitor terminals. If the battery is then removed and replaced by a load, the capacitor will discharge its stored energy into it. Let's now see how a capacitor reacts to an AC supply. Here we have our capacitor as before, with a Q plus and Q minus representing the charges. The AC source has a live and a neutral. We're now applying a sine wave. As the AC voltage goes through the positive cycle, it charges the capacitor. As the AC voltage goes through the negative cycle, it discharges the capacitor. This charging and discharging cycle by the capacitor disrupts the AC power flow. The value of this disruption is called the capacitive reactance. Let's look at how a capacitive load affects the current and voltage waveforms. Here we have the standard amplitude time graph. Let's add our voltage sine wave. Now let's add the current sine wave. The phase angle is the angular difference between the voltage and current waveforms. In a circuit containing a purely capacitive load, the current leads the voltage waveform by 90 degrees. Let's now look at that effect on the usual phasor diagram. Let's put the current vector first. Let's make it vertical as a reference point. Then the voltage vector, lagging behind the current. For a purely capacitive load, the current leads the voltage waveform by 90 degrees. Therefore, phi is 90 degrees. The power factor is cos phi. Therefore, the power factor is 0. Let's look again at the power relationship. Power is voltage times by current times by power factor. In capacitive load, the power factor is 0. Therefore, the power is 0. How can this be? Well, the capacitor discharges and charges over a full cycle, so no energy actually flows into the capacitor. In practice, all loads consist of some resistive and some capacitive elements, so the power consumed is never actually 0. When we have resistors and capacitors, all inductors, in a circuit, we call the resultant resistance to current flow the AC impedance Z. For a resistive capacitive circuit, impedance Z equals the resistance R plus the capacitive reactance XC. As XC is 90 degrees away from R, we give it a J or imaginary suffix. Therefore, Z equals R plus JXC. All three components are measured in ohms. Let's look at how to calculate XC, the capacitive reactance. XC equals 1 divided by 2 times pi times F times C. Well, XC is the capacitive reactance measured in ohms. Pi is the constant 3.14. F is the frequency measured in hertz. And C is the capacitance measured in farads. Let's do a worked example. For a 50 Hz system, what is the capacitive reactance for a 400 microfarad capacitor? XC is 1 divided by 2 times pi times F times C. Therefore, XC, putting the numbers in, is 1 divided by 2 times 3.14 times by 50 Hz times by 0.0004 farads, which is 400 microfarads. Therefore, XC is 1 divided by 0.1256. Therefore, XC is 7.96 ohms. One thing to note from the above is that as the capacitor value gets larger, its capacitive reactance reduces, and its effect on the AC system also reduces. Let's now look at the impedance relationships on a phasor diagram. First, let's look at the resistance measured in ohms. Let's make that a horizontal vector to represent a reference point. Next, we have the capacitive reactance, XC, also measured in ohms. And that's 90 degrees away from the resistance vector. Finally, we have the impedance Z, also measured in ohms. And that's the summation of the resistance and capacitive reactance vectors. Phi is the phase angle between the impedance and resistance vectors. By knowing any two of the above elements, Z, R, X, C or Phi, we can work out the value of the others using basic trigonometry. Let's now summarise what we've learned today. A capacitor is constructed of two parallel conductors separated by an insulator. When we introduce a capacitor into an AC circuit, it creates a capacitive reactance, which affects the power flow and power factor. In a capacitive circuit, the current vector leads the voltage vector. Congratulations for making it through 7 sections. I've attached some test questions in the course content. Please try them before going on to the next section, which will introduce inductors, another type of load which has an interesting effect on the electrical network.